Hey, good morning, class, and welcome to lesson 5.1.1. The objective today is I will be able to apply my knowledge of exponential functions to everyday financial and scientific situations. Recall the equation of an exponential model is y equaling a times b to the x, where y is the amount after x growth periods. So y is your output, x is going to be your input of number of growth periods. A is your initial amount, and b is the growth factor of greater than 1. So as you're looking at this equation, this is our general exponential growth equation. This is going to be modified in this lesson to fit different types of situations, sometimes scientific, sometimes financial. If we apply this model to situations where growth is an interest rate, then the exponential growth model may look like y equaling a times 1 plus r over n, all raised to the n times t, where y is the amount after t years, so t is our number of years, a is the initial amount, just like a in the first equation up here, r is the interest rate, and n is the number of times the rate is compounded per year. Now we're going to use this equation in our first problem. Multiple representations of exponential functions. Each situation below can be modeled with an exponential function of the general form y equaling a times b to the x. For each situation, explain why an exponential model can be used and create multiple representations, table, graph, equation for each situation before moving on. Verify that each representation for the situation is equivalent. We're not going to get into all of that. We're going to focus mainly on writing the equation, and we may take a look at a table. All of this, though, is given for a certain situation. Rommel has saved $4,000 and plans to invest it in an account that earns 5% interest. So now we've got our initial amount, A, and we have our interest rate, R, compounded quarterly, assuming no further deposits. How much money will Rommel have in the savings account after T years? And it's going to be compounded quarterly. So if Y is going to be our output value and 4,000 is our initial value, then we're going to take 4,000 times 1 plus our interest rate as a non-percentage decimal. So we have to divide that by 100. And we get 0.05 over the number of times it's compounded per year raised to the n, number of times compounded per year, times t. There's one way to write the equation. Another way to write this equation then is to simplify it a little bit. 4,000 times everything in here is 1.0125 times 4 to the t. There's an equivalent expression for this situation. Now we can even take this a little bit further. Remember, when you're multiplying in your exponent, that's like a power to a power. So we could write this as 4,000 times 1.025 raised to the fourth, and then all of that raised to the t. Now if I'm going to do all of that, then y equals 4,000, 1.025 raised to the fourth power is 1.1038 to the t. All of these are equivalent expressions for the situation that we are modeling up here. The first form is just a little bit more general to the formula on the previous slide. Every other one of these equations is then just a simplified form of the first. Additional practice. How long will it take an account to have $11,000? Ooh, it sounds like they just gave us an output value. If 5,000 is invested, so that's our A value, that's our Y value at 8.2 R compounded monthly. So let's set up this equation. Now we're still going to be using this idea of Y equaling A times 1 plus R over N raised to the N times T. So 11,000 is our output value. That has to equal our initial investment of 5,000 times 1 plus, convert this into a non-percentage decimal by dividing by 100. So I get 0.082 over N, which is compounded monthly. So that's 12 months raised to the 12 times T. Now, some of you may be wondering, okay, so where did this 1 come from in our formula? Well, that 1 is actually, you have 100% of this 5,000. And this is how much it's going up in a percent sense. So if you have 100% of something and it's going up by 8.2% every 12 months, then this is representing your overall growth factor. That's the B part in the general exponential growth equation. So now let's take and simplify this. 11,000 equals 5,000 times 1 plus 0.082 raised to the 12, or divided by 12, is 1.0068 raised to the 12t. I use that power to a power property. So we have 11,000 equaling 5,000 times 1.0068 raised to the 12th power. And all of that is then raised to the t power. Now if I take 1.0068 raised to the 12th power, I now have 11,000 equaling 5,000 times 1.0852 to the t. Now we need to solve for t. So I'm going to divide both sides by 5,000. Let me erase this. So I have 11,000 divided by 5,000 equaling 1.0852 raised to the power of t. 11,000 divided by 5,000 is 2.2, equaling, and I'm going to leave a little room here, 1.0852 raised to the power of t. At this point, this goes back to your algebra 2 now, we're actually going to take the log of both sides. By taking the log of both sides, that allows us to pull that exponent out in front. And so I have the log of 2.2 equaling t times the log of 1.0852. Now divide both sides by the log of 1.0852. And if you divide this on your calculator, t comes out to be about 9.64 years. Now when you divide this on your calculator, when you take the log of 2.2, make sure you put parentheses around the log of 2.2, then your division sign, and then the log of 1.0852. Now I want you to take these skills and answer the next question. Pause it before you do that and then come back and check your answer. So the equation that you get for part C is going to be P times 1 plus R divided by 100. Remember, when you take that percent, just like we did in the last problem, you have to first divide that by 100 over n raised to the n times t. That was an application of our skills to the financial world. Now let's apply this to a scientific situation. Atmospheric pressure is the pressure exerted by the weight of air in the atmosphere of the Earth. It is caused by the weight of air above the measurement point. As elevation increases, there is a less overlying atmospheric mass, so that the atmospheric pressure decreases actually with increasing elevation. At sea level, 0 feet elevation, the atmospheric pressure is 101 kPas. That's kilopascals. For every 500 feet of elevation gain, the atmospheric pressure decreases by 1.8%. What is the atmospheric pressure at an elevation of x feet? Now here, we're going to have to address a couple of changes from the previous problem. We still are going to be writing an equation where y equals our initial amount, so I'm just going to call that A, times 1, but now we're decreasing. So that means we're going to have to subtract instead of add. Previous problem, we were increasing by 8.2%. In this problem, we're actually going to decrease by 1.8%. So this becomes 1 minus your rate divided by 100 raised to the x over n. In this case, n is going to represent 500 feet, because in the problem it says for every 500 feet I'm going to end up compounding 1 time. So let's just build a little bit of a table and take a look at what I'm referring to. So if x is the number of feet, and if x happens to be 500 feet, or 1,000 feet, or 1,500 feet, then my exponent, which is going to represent the number of times I compound. If I go up 500 feet, I want my exponent to be 1, because that means I'm going to take my initial value, A, I'm going to multiply by this growth factor, or in this case, excuse me, this decay factor 1 time. If I go up 1,000 feet, I want my exponent to be 2, because I'm going to multiply by this factor 2 times. If I go up 1,500 feet, then I'm going to multiply by this factor 3 times. So each time I'm taking the number of feet, x, and I'm dividing it by the value 500. R is your interest rate. Y is your air pressure in kilopascals. And A is your initial amount of air pressure. So in this case, Y equals my initial air pressure of 101 times 1 minus my rate of 1.8% divided by 100, so 0.018 raised to the x over 500. Now if I simplify this, y equals 101 times 0.982 raised to the x over 500, which can also be written as 101 times 0.982. We got a little bit of a power to a power up here of 1 over 500 raised to the t. Now if you take 0.982 raised to the 1 over 500, so on your calculator that would look like this. If you type in 0.982 caret parentheses 1 divided by 500, you're going to get 0.99996 raised to the t. All of these are equivalent ways to model this situation. Another scientific application of our exponential modeling. A scientist is growing bacteria starting with a culture of 5 bacteria. Grown by multiplying. After 2 hours, there's 14 bacteria. How many bacteria would be present after t hours? I'm going to start by actually building a table. T is number of hours. Y is going to be my output value. And so after 0 hours, I have 5 bacteria. After 1 hour, I don't know. But after 2 hours, I have 14 bacteria. After 3 hours, I don't know. After 4 hours, I don't know. I got to try to figure out what this growth factor is. So let's start by writing y equaling a times some value b raised to every 2 hours I am multiplying by my growth factor. So I'm going to raise this to the 2 over t, just like in the previous problem where we had x over 500, because it was for every 500 feet we were decreasing by a certain amount of air pressure, or kilopascals. Here, for every 2 hours, we're going to be multiplying by our growth factor. My a value is 5. So my equation I know is going to look like this. 5 times b raised to the t over 2. Now let's try to figure out what b is going to be by using this second point that we have, this 2 over 14. So if t is 2, then my output happens to be 14. So let's write this as 14 equaling 5 times b raised to the 2 over 2. Well, 2 over 2 is 1, so I have 5 times b equaling 14. Divide by 5, and b comes out to be 14/5. Or as a decimal, b is 2.8. So my equation, y equals 5 times 2.8 raised to the t over 2. Now what I want you to do is pause this and write this equation in two equivalent forms, and then come back and check your work. Okay, welcome back. Here are two equivalent equations. Again, you got this little power to a power taking place, so you could write this as 2.8 to the 1/2, then raised to the t. Then if you take 2.8 to the 1/2, you're going to get 1.673. So 5 times 1.673 raised to the t would be another equation. Last problem for the day. Julie has a fresh cup of hot coffee that has a temperature of 180 degrees Fahrenheit. The temperature of the room is 70 degrees. We want to sketch a graph of the temperature of the coffee over time. Now this graph is going to be just a rough sketch. It doesn't have to be super specific. We just want to get an idea of what is really taking place here. So I'm going to draw this in here, my y-axis and my x-axis, and I'm going to say that this happens to be right up here at about 180 degrees, and it's going to go down to about 70 degrees, which would be somewhere right about in here. Now, as it's cooling to 70 degrees, theoretically, if this were to be an exponential decay situation, this is going to keep getting closer and closer and closer to this horizontal asymptote of 70. So this is what our graph would look like, where hours is on the x-axis and temperature in degrees is on the y-axis. Now let's write an equation for this situation. T is the number of minutes after Julie pours her coffee. Y is going to be the temperature of the coffee. Now 5 minutes after Julie pours her coffee, the temperature is 160 degrees. Write an equation to model the situation. So let's plot this point of 5 minutes at a temperature of 160 degrees. First thing I need to do is erase this hours, because it's actually minutes on the horizontal axis. And 1, 2, 3, 4, here's 5 minutes. And let's just say after 5 minutes, this temperature is 160 degrees. Now remember, this is not drawn to scale. Well, if we are going to assume that this is an exponential equation, so y equals a times b to the x, then there's going to have to be some type of vertical shift of k, because all exponential equations, exponential decay equations, are going to approach the x-axis and have a horizontal asymptote on the x-axis. This equation doesn't. This equation has a horizontal asymptote 70 units above. So if I was to take every one of these points and shift them down 70, this point would become 5 comma 90. This point shifted down 70 would be 0, comma 110. Now let's find our initial value and growth factor for this blue graph, A times B to the X, or not growth factor, but decay factor. So this is going to be our decay factor. This is going to be our initial value. Well, the initial value we know is 110. So my equation right now is y equaling 110 times b to the x. Well, here is an x value, here is a y value, and if I plug those into my equation, I can then find b. So I'm going to put 90 in for y, equaling 110 times b to the 5th power. Divide both sides by 110, and 90 divided by 110 is 0.8181. Equals b to the 5th power. Now you could take the 5th root of both sides, or I'm hoping we're developing better exponent skills where you could say, hey, I'm going to take both sides and raise it to the 1/5 power. Because 5 to the 1/5, you multiply, you get 1. So this is b to the 1 equals 0.818 raised to the 1/5 power is 0.961. Now let's go 0.9607. 0.9607. Those are our A value and B value for the blue equation. So 110 times 0.9607 raised to the x power. We want to find the actual equation for this temperature of coffee as it approaches the room temperature of 70 degrees, where this is our horizontal asymptote. It's going to be the same A values, 110, same B value, 0.9607, but now we have that vertical shift of 70 units, so I'm going to put plus 70 at the end. Our equation for the temperature of the coffee, given x in minutes, is 110 times 0.9607 raised to the x plus 70. We're going to jump to part D and answer that question. What is the temperature of the coffee 15 minutes after it was poured? So this is for the black graph using the equation with the vertical shift. So y equals 110 times 0.9607 raised to the 15 minutes plus 70. So y equals 130.285 degrees Fahrenheit. Okay, class, welcome to the last question in our lesson, where we talk about half-life. An important application of exponential functions lies in the calculating the intensity of radiation from radioactive isotopes by using a mathematical model. Most isotopes emit particles and decay into stable forms. The amount of decay of the particles can be described by the isotope's half-life, which is the amount of time it takes half of the isotope to decay. For example, the half-life of bromine 85 is 3 minutes. If you start with 60 grams of bromine 85, 3 minutes later, 30 grams will remain. how much bromine 85 will remain after 20 minutes? Well, what we're actually going to do here is we're going to just write the equation to help actually answer this accurately instead of just estimating. Even though estimating is a very important skill because it allows for problem solving, we're going to get down to the brass tacks of getting an equation for this. Of y equaling our initial value, A, times a decay factor of B raised, we're going to be thinking about this. This is going to be x divided by 3 because it says for every 3 minutes. So that means if x is representing the number of minutes, and y is the amount of bromine, then if we have 3 minutes of time that have transpired, then this exponent would be 1. We would be multiplying by b one time. If x was 6, x is 3, 6, 9. Our exponent, which is the number of times we multiply by our growth factor, would be 1, 2, 3. A represents the initial value, which is 60. So y equals 60 times the net B value. That's our rate. Remember, every 3 minutes, half of the bromine is going to remain. So my B value is 1/2 raised then to the x over 3. So if we have 20 minutes that has transpired, I'm going to take 60 times 1/2 raised to the 20 over 3, which comes out to be 60 times 0.0098. So then y equals 0.59 grams of bromine after 20 minutes. So the overall equation, if we want to try to write equivalent forms of our equation, y equaling 60 times 0.5 raised to the x over 3, well, y comes out to be then 60 times 0.5 raised to the 1/3 raised to the x, which is also equivalent to y equaling 60 times 0.7937 raised to the x. All three of these equations are equivalent to each other in ways to write this exponential decay model. Hopefully you enjoyed this lesson. Remember, Friday is your Chapter 4 test. There's a lot of review material and activities that have been spread out throughout this week. Please engage in those, from exit slips to the homework to the review packet. Also, please utilize the Zoom meetings with your teacher. Wishing you all the best this week. Have a good one, and we will see you next week with Lesson 5.1.2.